About trigonometric forms of complex numbers. So that's our lesson for today. Okay. And our objectives for today are we want to learn how to plot numbers in the complex plane. Yeah, okay, that one. Second objective is to learn how to write trigonometric forms of complex numbers. There's some ugly forms. Yeah. Hideous. Third objective is how to multiply and divide complex numbers. Fourth is how to use Demoivre's theorem. Hold on. Right. Having a bad day handwriting this morning. It's an R. Hold on. There. How do you use Demoivre's theorem to find And last objective is, of course, to find nth roots of complex numbers. Okay. So, unfortunately for us, we have learned number theory backwards. And so they've taught you how to graph real numbers, when in reality, they probably should have taught this first. So our first objective is how to plot. And since unfortunately they taught you this backwards, this is going to seem a little bit counterintuitive. So every number that exists is actually a complex number. It consists of two pieces, a real piece and so-called imaginary piece. So let's first define what a complex number is. Okay. A complex number is a number that has real piece, an imaginary piece. I put imaginary in quotation marks. And that's a reason for that, which we'll discuss a little bit. So, when we speak of imaginary, we're not speaking of something that isn't real. It was mislabeled when Gauss and the others that came up with imaginary numbers. It was mislabeled. It's called imaginary, but it's completely real. So you'll recall that all numbers forms that exist are what we call complex numbers. All numbers that exist are complex. And from within that, we have real numbers, and so within that piece we have reals, we have and then we have rationals, irrationals, but I'm not going to go over that. So, but the idea is that there's two pieces to a complex number. And this is all review. This is all going to be in the chapter 7 review. Yeah. Send it, open up again. The system crashed. Go figure. That's okay. And so, when we're working with complex numbers, we have two pieces, the real piece and the imaginary piece. And in the real piece, those files. And we were over here somewhere, I think. Right here. Okay. So that, well, the whole number theory thing we're talking about complex numbers. So you have real piece and imaginary piece. So yes, we have defined what a complex number is. Okay. And so we call imaginary in quotation marks because it's not imaginary as in fake, but we used image in a more literal sense in this case. And we'll talk about the word derivation later. And so all complex numbers, this is all review, of course, from our earlier lesson on complex numbers. We have complex numbers, which you guys learned in Algebra 2. Any number z is equal to a plus bi, where we define z as the complex number, and of course a is the real part, and of course bi is the imaginary. Put it in quotation marks again. Okay. And so, to graph on a complex plane, we need to have a plane to do this in, and so we do that like this. You have to deal with my horrible graph. And so our x-axis is the real axis, and the y-axis is the imaginary axis. Okay. And any point on this graph, so we'll place it right over here, for example, is the point AB, like this. And AB represents an imaginary point. So this is point, call that B, we'll call this A, and so A comma B is the same as A plus BI. Okay? Everybody see that? That A, we go A points along the x-axis, and B points along the y-axis. We add them together, and we get A equals BI. And this distance, you'll notice it forms a line like this. We'll call that distance R. We'll call that distance R. And that R represents what we call absolute value or modulus. Okay, so I'll write this on the next page. The modulus is the absolute value of a complex number. And the absolute value is, of course, the distance from 0. It's how far away you are from 0, just like in real numbers. Now, that said, going back to my picture, like that, we have this r. How do we get it? It appears as if it forms a triangle, right? The r, this length, like that. You have b, and you have a. And you have a right triangle, angle theta. And since you have b and you have a, r, the length of r is going to be dictated. I'll write this on the next page. R squared equals a squared plus b squared. And simply put, thus from here, r is equal to square root of a squared plus b squared, like that. And this is the modulus, or the r, as your textbook uses. I'm not erasing the formula. Well, I am erasing it. I'm going to rewrite it. So the absolute value of the complex number is, of course, the radius, which is another symbol for r, which is square root of a squared plus b squared. Okay? So how do we plot numbers on the complex plane? So, for example, let's do our first example. I'm going to plot 3 plus 2i and find the modulus. Okay. So to plot 3 plus twice I on the complex plane, simply put, for part A, we create our graph. Okay. 1, 2, like this. Using arrow, something like that. Alright, so this is our plotted on the plane. You could just use it as a point, but I prefer to use the arrows. And you'll figure out why later. We'll talk about why that is later. And so to find the modulus, r, going to be the square root of a squared plus b squared, which is, of course, square root of 3 squared plus 2 squared, which is 9 plus 4, and square root of 13. So this is r. Your modulus is square root of 13, and that's units. Okay? Now, that's plotting numbers in the complex plane. And so now, from this graph, I want to derive our forms for the complex, for our trigonometric form. Because simply plotting numbers on the plane is really easy. It's going over your real piece, then your imaginary piece, like that. So now we're going to derive the formulas for trigonometric forms of complex numbers. So that's objective 1. On to objective 2. In 2, we are, of course, doing trigonometric forms of complex numbers. Okay, so now, using our graph that we had earlier, we have a real piece. This is our point A comma B. Okay, this is our point A comma B, which, as you know, is A plus BI. Now, we have an angle that's formed here. It looks like a right triangle. This is your angle theta. This was R. We defined that to be R. We defined that to be B, and we defined this to be A. And if I use the ratio of triangle in this situation, I have sine and cosine, of course, which, as you know, is sine is y over r. So in this case, sine of angle theta dv divided by r, and of course cosine of theta goes a divided by r. And from here, I want to solve for a and solve for b. So I know that a is equal to r cosine of theta, and of course b to r sine of theta. From here, I just substitute it back into the expression. Z equals R equals A plus BI. And of course, A cosine theta plus R sine of theta. The R factors out RI sine of theta. So the R, because it's in common, factors out. So we end up with R cosine theta sine of theta, and this is Z. And this is the trigonometric form of complex number. I'm going to write this on the next page. The definition of complex number is going to be where Z is equal to R cosine of theta plus I sine of theta. And we recognized R from earlier. Okay. Recognize R from earlier, which is called the modulus. So this is going to identify the pieces. R is the modulus, or the absolute value. We define theta is the argument of the angle. And one thing I did not show you, and this should be relatively obvious, from here, if I wanted to solve for the angle, I could use the ratio of tangent to theta in this situation. I could use that tangent of theta is equal to b divided by a. And so, therefore, where's z? And we remember the formulas from earlier. We know the formula of r is equal to square root of a squared plus b squared. And then we end up with theta, or tangent of theta, equals b divided by a. Or I could write that theta equals arctangent of b divided by a. Of course, a cannot be 0. Okay? So far, so good. Everybody with me? Great. Now, let's convert it. Let's convert a regular complex number into its trigonometric form. So let's do an example of that. How to do that. So convert z equals 1 minus I into its trigonometric form. Okay. So first we need to identify A and B. So using we know that A is equal to 1, B is equal to -1, and so we want to solve for its modulus. So we solve for the modulus. So the modulus is going to be r square roots a squared plus b squared square root of 1 squared plus -1 squared, which is square root of 1 plus 1, which is square root of 2. Now that we know what r is, we need to know what the angle is. And so from here we find the argument, or we find the angle. Okay, step 1 is to find the modulus. Step 2, find the angle. So theta equals arctangent of b divided by a, which is arctangent -1 over 1. So from here I know that theta, its inverse tangent. Inverse tangent has its domain. So it's going to equal -pi divided by 4 plus or minus n pi. So -pi over 4 will be the angle that we use for that. But there's a problem here, of course, as you can see. So the problem here is that this trigonometric number is in the third quadrant, because, or fourth quadrant, So, since the number is in the fourth quadrant, cosine will be positive and sine will be negative when you plug this number in. So you can leave the angle as such, but we're going to use the positive angle. So if we add So if we add 2 pi to that angle, if we add 2 pi to this angle, we're going to get 7 pi divided by 4. Okay. And that's the angle that we'll use. It doesn't matter, I could have left it as negative pi over 4, but it's sometimes easier to work with the positive angle. So that's what we'll do here. And now that we know all the pieces of the puzzle, we can simply plug it in. So from here we use our z is equal to r cosine theta plus I sine theta. So it's going to equal r, which we found is square root of 2. And we just say cosine of 7 pi over 4 plus I sine of 7 pi divided by 4. And this is our z, and that's all there is to it. We don't really need the parentheses there, I just put it there for emphasis, I suppose. So that's how we convert it from the standard form to its trigonometric form. Now, if I distribute it to the negative, if I found out what these values were, I could go backwards. Now, didn't plot that on 4. Now, to go backwards, I would simply take that 2 and distribute it. So, to go backwards, I'm going to distribute the 2, the square root 2. Cosine of 7 pi divided by 4, fourth quadrant, it will be positive. So this will be square root 2 over 2 plus sine of 7 pi over 4, which will be negative square root 2 over 2 because it's in the fourth quadrant. And then from here you distribute. To distribute it, you go backwards like that. So this becomes 2 over 2 plus negative 2 over 2, which is 1 minus I, as we found, as the original problem stated. Okay? So you go backwards by just distributing it amongst the pieces that you have. Okay? Everybody good? Sweet. Okay, so that covers our second objective. We will cover objectives 3, 4, and 5 in the next video.